Okay. So what we've seen in the past few years, it's a shift in the way we communicate over the internet in terms of security. So we've seen HTTPS being enabled by default on most major websites. Then we have seen the advance of using opportunistic encryption rather than using no encryption at all. That is, let's at least encrypt, even if an adversary could perhaps compromise the keys through executing a kind of man-in-the-middle attack, but let's at least avoid those passive attackers that cannot do that. And this is under standardization. It's kind of waiting at the moment, not sure what's going to happen, but the process has started. And we, or most of you at least, use this application called WhatsApp, which relies on a kind of trust on first use authentication, because you are trusting that first key exchange that you do initially before continuing the conversation with the other person. So we see all of this going on. However, there are issues. First of all, HTTPS can be broken if certificates are compromised, and we've just seen in the previous talk that there are many possible attacks, like, for example, messing up with the DV validation. Then opportunistic encryption, as it was designed, basically doesn't protect against any kind of active adversaries, because it's doing only a simple Diffie-Hellman key exchange. And tofu-based protocols are vulnerable during the first contact, during the first exchange. So if an attacker is able to compromise your first connection, the entire security is gone. So now SMKEX can help in all of this. It can improve the security on all of these protocols. But to give you some idea of the problems that we are trying to solve, the main problem is related to the fact that on a key exchange, we may have some adversarial in the middle, as you must know. So in an ideal case, Alice and Bob are trying to communicate to establish a secret key, and they just exchange some messages, and they end up with the same key. However, in the more realistic scenario, we have this adversary, which could be a nation state adversary, or maybe your organization who wants to snoop on your traffic or something like that, and it's able somehow to make the adversaries believe they have exchanged the key, but actually the adversary has access to all the communication. So TLS came to the rescue with the use of certificates. Basically, in this key exchange between Alice and Bob, Bob, together with his public key, is also sending a signature over this key, which is validated through a certificate, and then Alice, receiving this signature, is able to verify that this signature was indeed generated by Bob, and so is trusting that it's actually communicating with Bob. However, as shown in the previous presentation, an attacker could somehow compromise their certificate, break into their servers or something else, and issue a rogue certificate. That is, issue a certificate for Bob, while Bob was not actually desiring to provide that certificate to the attacker. And again, we are back into the case where the users do exchange a key, but they are not actually communicating with the desired party. So what is our idea? So our idea is to try to exploit the fact that in practice, we may have multiple public channels available. So not channels that are secured in any way, like visual channels or other channels, just public channels, but there may be multiple. Think of the practical example of your mobile phone. On your mobile phone, you have usually at least two different interfaces. You have the wireless channel, which you are probably right now using here in the conference, and you may have also the mobile carrier, Orange, Vodafone, Verizon, whatever you have here. So this might be operated by two different operators. So you are going through two different ASs and so on until you reach your desired server. So this is the context in which we are trying to improve over the existing security. But before I go on, we need to detail the attacker model that we consider. So we consider several types of attacker, and please see the paper for more attackers than those that I'm focusing in this presentation. One of them is the all-powerful attacker that can control both communication paths, and in addition can also communicate synchronously, that is live, doing the protocol execution across these channels. So this is an attacker that can do anything in the network, basically. Can inject packets, can communicate across the channels, controls both channels. This is a very powerful attacker against which we cannot do much compared to the existing solutions, because it just reduces to the standard one-path attacker. So there is no difference. However, we can also consider slightly weaker attackers, in which we have active attackers on both paths, but they are not able to communicate synchronously during the protocol execution. And for this particular case, our protocol is proven securely. And it provides a secure key exchange. And I'm going to try to convince you that there are many practical scenarios in which this model makes sense. It holds. And we can even enforce it in some scenarios. And again, see also the paper for some other models for which our protocol is secured, like, for example, having a passive adversary in one path and an active in the other, and they are able to communicate. But I'm not going to focus that just for brevity. So here is our protocol in a nutshell. Basically, we are using two paths, although you could use more than two paths if you want. And on the first path, we just do a standard Diffie-Hellman key exchange. Of course, here you can use elliptic curves, that's fine. This is just for exemplification. So on the first path, we just have a standard Diffie-Hellman key exchange. And on the second path, we send some nonces together with a hash over all of these public values. That is, over the public key values and over the nonces. So that's what is being sent on the second path. Now, this seems very simple. Indeed, it's very simple. Some of you may think it's trivial. However, I can assure you this is the result of several years of thinking of this. We thought of many other variants which turned up not to be secure. And please look at the paper for why other things like using secret sharing are not providing the same security features as SMKEX. And secondly, the fact that it's simple is actually a very good thing, because it means that we can very easily combine SMKEX with many of the other security protocols for securing communications, like tofu-based approaches or TLS and QUIC. Okay, and very important, we don't need any certificate authorities, pre-established keys, or any other of these things. So it's just using public channels, and that's all we need. Okay, so as I mentioned, the very interesting thing is that if we are in this context where we have unsynchronized active adversaries, SMKEX is proven to provide a secure key exchange, and you can see the proofs in the paper. And the main intuition behind that is that an attacker that wants to mess up with the public key values is not able at the same time to modify the hash that is needed on the second connection. Basically because we modeled the attacker as not being able to communicate across the two paths during the communication. And so you can think as the fact that basically there is no way to get those public key values across. Furthermore, as the design of our protocol doesn't use any long-term secrets, we automatically provide forward and backward secrecy by design, basically. Okay, so now you may be thinking, okay, let's see why this kind of attacker model makes sense. So let's see why this unsynchronized attacker is actually realistic. So we made a measurement study across 5 countries. It's not, let's say, an exhaustive measurement study. It's an initial measurement study. Feel free to go ahead and try it on more countries. We're happy to get your feedback. And we wanted to see when communicating over this kind of 2 channels on a mobile device, like the mobile carrier and a fixed network, when connecting to the top 100 Alexa websites, how much path overlap we get in the middle. So that is how many of the autonomous systems between our ISPs and the remote server are common across the two paths. And for this, we did the following. We took the first path, let's say the mobile carrier, and we ran traceroute from our device to each of the servers. And we computed the set of ASs that are in the middle. Then we did the same for the other connection, for the fixed connection, and we computed the set of ASs that are in between. And then we computed the intersection of these 2 sets. And then we get 2 possibilities. Either we have no overlap, that is, we get an empty intersection. Either we have some overlap between 1 or more ASs. And the results are quite interesting. So for example, here I show you the results for 3 out of the 5 countries we tested. We can see that for the best combination of mobile and fixed networks, we already get between 50 and 70 out of the 100 websites for which we have no path overlap. And this is with the current infrastructure. So you don't need to do anything. Just run SMKEX, and you get already between 50 to 70 websites for which SMKEX is going to provide you security against what we call local attackers. By local attackers, we mean attackers that can only control one of the networks, either the mobile network, so the ISP of the mobile network, or the fixed network. So these are the local attackers. So against these attackers, SMKEX can already provide security. And for the worst case, for the worst combination of mobile and fixed networks, for example, for Romania, we still get about 12 websites for which you get, again, no path overlap. However, even for this, let's say, worst case, where we get only 12 websites, we can rely on things like Akamai, content distribution networks, to actually reach websites that use CDNs with no path overlap. So we looked for the case of Romania, and we look at all the combination of mobile and fixed operators to reach the Akamai servers. And it turns out that we have actually no path overlap with any combination whatsoever between mobile and fixed operator, which means that for any website that is hosted through Akamai, SMKEX is again going to provide security against local adversaries. Okay, we can do even more than that. We can actually enforce the unsynchronized scenario. That is, we can enforce having no path overlap between the attackers through the following quite interesting mechanism. Let's use some encrypted tunnels between the user that wants to communicate. So we have here our user Alice and the service Bob in Europe. And now Alice is going to create an encrypted tunnel using some virtual machine in North America. We used, for example, machines in US, but you could have here one in Canada. And then we expect also Bob to have a service accessible in that part of the world. For example, Bob can also have a service provided here in Canada. And this is most commonly for major websites. Microsoft, Google, Facebook, and so on, they will have replicas. And most websites using a CDN will have replicas across the world. So this is kind of a common scenario. So now, looking at this picture, we can see that the connections are secure in the encrypted tunnel, because that's something we assured ourselves, and they are secured in the VPN of the service. So all we need to assure is that the attacker cannot basically attack the public path in Europe or the public channel in the States or Canada. So that's what we want to guarantee somehow, that we cannot have an attacker that is able to synchronize on this. So for this, we can basically use an idea from alibi routing, which was proposed a few years ago at SIGCOMM. And this goes as follows. Let's compute the round trip time on the local path that is in Europe. Let's see how much it takes to make a round trip on this communication channel. Then we compute the round trip time on the other link, on the remote link in North America. And then we also compute what is the expected minimum round trip time at the speed of light between our two endpoints. So we can do that geographically. We just use Google Earth, we look at the distance on the map, and then we assume speed of light, and we see what would be the minimum round trip time for an attacker. And this would be a minimum physical bound. An attacker could not do faster than that, because unless he has some very ingenious ways to go faster than light. But well, that's an assumption. So if that's the case, those are the measurements. Basically, if the sum of the two RTTs on the paths that are attackable is smaller than the RTT estimated between the two endpoints of the user by the speed of light, we have a guarantee that there is not going to be any path overlap between the remote path and the local path. And this is a physical bound guarantee. So then we went on and measured what is the fraction of websites for which we can guarantee no path overlap. So for which we can guarantee that the paths are disjoint using the alibi method presented above. And what we see is that when we use a fixed connection for which we have low latency on the local link that is in Europe, we see that for all the countries we tested in Europe, that is for UK, Switzerland, and Romania, when using a virtual machine in the States, in Virginia, we have about 50% of the websites for which we have a guaranteed non-overlapping path. So this is 50% of websites for which we are sure that an attacker cannot have overlapping paths. So this gives us the possibility to say that SMKEX provides guaranteed security against adversaries that can only attack either servers in the States or servers in Europe, but not both. So this would work basically against any adversary that is not able to control both America and the States. So if you are like a super state that somehow you are able to control both networks, then there's not much we can do. But this is what we can guarantee, basically. And again, this comes almost for free. The only thing that we needed for this solution is that the user makes this virtual connection to some virtual machine across the Atlantic. But one thing to mention here is that you only need to do this connection once, and then you use it for any server you connect to in the world and forever. So you need to do that once, and then you connect anywhere and anytime. Okay, now, since we said that SMKEX is very simple and can be integrated with other protocols, let's give some examples. So one of them is integrating with tofu-based approaches. So for example, here you could just store the server key at the client side, and this would already improve the security of tofu-based approaches, because an attacker would have to attack both connections during that first exchange. So we're making it very difficult also for this. Basically, we are improving the security of tofu by increasing the difficulty of attacking the protocol during that first exchange. Then it's also possible to integrate SMKs very easily with TLS or QUIC, and we get the both of best protocols. Basically, for TLS, we get this enforced identification through the certificates, and of course, we get the fact that it's widely deployed, so most people are using it. For SMKEX, we get protection against these ROC certificates, as was shown before. So basically, we can detect a local or national powerful adversary when trying to use ROC certificates. And we are already working towards standardizing this. So we're working towards discussing this into the standardization bodies of Multipath QUIC. Just to give you a quick overview of how this could be integrated very easily. Basically, when using TLS, we just need to do the standard client hello and server hello exchanges on the first path. And then on the second path, we send the hash over the public key values together with these nonces that we took from the first path from the TLS standard TLS exchange, and we move them to the second path. We have implemented SMKEX in the following way. For our evaluations, we've used two core components. We have used a user space library that overrides part of the socket API. That is, we override the connect and accept functions mainly, so that any application can just preload our library, so that when you run connect or accept, you're going to run our protocol under the hood. So you don't need almost any modification. And then we also use an MPTCP enabled kernel with some minor modifications. MPTCP, which is Multipath TCP, allows you to create multiple connections for the same TCP connection, basically. So you run a single connect accept socket. So you run, basically from the application level, you are running one connection, but under the hood, you're actually running several TCP connections, which allows increased reliability, robustness, and so on, but can also be used to basically implement out of the box our protocol, because you've seen that we need these two paths. And what we did was to patch a bit the existing MPTCP implementation so that we can select which of the paths we use for sending the packets, because you've seen that we need to send the public key values on the first channel, and we need to make sure that these are both sent on the first channel, and we need to send that hash on the second channel. So we need to be able to choose which are the paths on which we send the different messages. We have also measured what is the performance impact of SMKEX compared to a standard DV-Hellman, and the impact is minimal. Basically, the extra time is one round trip time, which at the moment is introduced by our MPTCP implementation, which requires one extra round trip time to create the second flow. But this could be sorted out in the near future by just tweaking a bit the implementation and not waiting for that extra round trip time and just starting to connection, basically. So it's something that could probably be engineered in the near future. So in conclusion, SMKEX increases the security of opportunistic encryption. That is, it can already provide protection against local and national adversaries without requiring any third trusted party or established secret keys. It can also be integrated with TLS, QUIC, or TOFU-based protocols, and by providing, so it provides best of both approaches. And what is very interesting is that the existing infrastructure already enables the use of SMKEX right now. So you can use it basically for free. I mean, in the worst case, it's going to be just as without SMKEX, but in the best case, you are going to protect against these local and national adversaries. So you lose almost anything. You don't lose anything by using it. Besides that extra round-trip time for the current implementation, but which could be engineered away. So you get it almost for free. And we have our code open source. You can go ahead and try it. And please see the paper for many more details regarding the implementation and how to implement it when using a CDN. If you want to use that virtual, encrypted tunnel approach, you can see there all the details that you need to actually make it work, and also for security proofs. And just before I conclude, this is our team. So as I mentioned, this was work done mostly at the University Polytechnic of Bucharest. I'm Marius Chaudhry, and thank you very much for your attendance.
Any questions from the audience? If you have questions, please step to the microphone and say your name and affiliation.
Tudor Dumitraș, the University of Maryland. Great work. I'm curious, it's probably in the paper, but can you explain how this protocol would help in the case of in the case of man in the middle with the forged certificates?
So the idea for certificates is that if you use a RAG certificate, then basically your attacker would kind of try to fool you on one of the paths by sending a certificate. But if he's not able to communicate synchronously with the other path, he would not be able to compute that hash that you need. So basically, when you integrate, basically it would be that integration from here. You'd get the standard TLS running on the first channel, and on the second channel, the attacker would have to compute that hash value, which in the case that the attacker is not able to control the second path, he's not able to compute that hash value.
So you get two certificates on the two paths, that's the idea? It
would be just one certificate. So it would be one certificate on one path, but that attacker that is able to fake that certificate would not be able to also fake that hash value. That is, he would not be able to compute the hash value that is needed to actually make the protocol work.
Hi, this is Setare from University of Calgary. So my question is that do you need the channels to be independent or can be correlated? Like the path in the model?
I'm not sure I understand the question. If you can provide some more details,
you have
please.
two paths or channels like the example you gave. So do you need those channels to be independent or there can be correlation between
So
them?
what do you mean by independent? That's what I'm not sure in practice. What do you mean by independent in practice?
Do you need to ensure that the output of each channel is not affected by the other channel or not?
Sure. So in that sense, yes, because that's what we assume by the fact that the adversaries are not able to communicate.
Okay, so in this case, maybe other than the example you gave, I couldn't come with other examples where we actually have different independent channels. So like, because in the environment you may have different channels, but usually these channels are correlated. So in practice, how can you solve this problem?
So for the moment, we just thought about the solutions we presented, but it would be very interesting to think about other solutions. So if you like this and you want to look into it, please do so, and we're happy to help. So
okay.
Yes, but yeah. Yes, we are looking for more ideas. Yes, thanks.
More questions? Yeah, maybe I can ask one. So, how about the limitations regarding to SMKEX? Can you talk a little bit more about that?
Right. So one of the limitations is that it doesn't protect against an adversary that can communicate across the channel. So as I mentioned, if you have a null powerful adversary that can actually communicate synchronously, there is not much you can do. You are back to the standard Diffie-Hellman key approach in a single channel. So you are back to whatever can be done on that can be done against this one. So that would be the main limitation. So it depends if you are in that scenario where the attackers can communicate or cannot communicate. If they cannot communicate, basically we have a proof that this just works. Of course, it's also possible that in our proof or our model we missed something from the reality. So who knows? Maybe as some of the talks said in the crypto sessions, our model is not perfect, is not capturing everything. This could be one of the limitations. Yes.
Hey, Luke Valento, University of Pennsylvania. Did you also consider in the paper extending it to like end channels?
Yes. So you can see in the appendix of the paper, it's very easy. Basically, all you have to do is send the hash on the other channels. That's so it's quite easy to extend. Yes.
I was just wondering how widely deployed multi-channel TCP is, or how easily available that is.
Right. That's a very good question. So it has been. It's an ongoing work, actually. Apple has already introduced this in some of its services. So if you have an iPhone, you are already going to have multipath in the kernel of that phone. Linux has already multipath as an option. Not sure if it's enabled by default, but you can easily enable it. And I think there are some operators, like for example, there is a Korean operator that is using multipath already in its services to provide improved reliability. So it's getting more momentum and quick, actually. It's working, it's already started standardizing a multipath version. So it's an ongoing development, and hopefully SMKEX, if people like it, may also help to improve this development, because I said it comes almost for free. So if you get MPTCP, SMKEX is kind of free addition to improve security.
Yeah. In your measurement studies, when you say that there's no overlap to, say, some SDN, are these different servers from the same SDN that you end up connecting to?
Right. So I should have mentioned, sorry for that. So I'll go back to the slide to clarify a bit. Let's see, where was that? Okay. So I'm missing the slides. This one, yeah. So indeed, basically, often the CDNs are going to have different edge servers. So for each of the connection, they are going to terminate the connection on that link. That's which is very useful for our protocol. Yes. So basically, when you're going through the mobile connection, the CDN is going to terminate the TLS connection there. And you are going to the fixed connection, they are going to terminate the connection on that.
But don't they have to communicate internally then? Or?
They communicate internally, and actually we show in the paper a way to do the necessary communication to pass the parameters needed to actually make the link between the connection on the back. So there are some engineering solutions that are already in place. So there is a paper, I think it was at NDSS last year, that shows precisely how to do this, and the technology is called Beamer. And this is something that was actually developed in our university, quite an efficient way of how to do that.
More questions? Okay, let's thank Manos one more time.